Good morning, students. Today we're going to work on a new topic, and this will be the last topic of the school year, and that topic will concern parametric equations. And we're going to work first on graphing parametric equations. So what we want to do, first of all, is we want to define what a parametric equation is. A parametric equation is when your variables of a function are described by another variable. Okay? So they depend on another variable. An example of this would be, would be something like this. Suppose you have two variables in a function. The variables are x and y. And suppose those variables depend on some other variable, say time. Then these variables would be functions of time. In calculus, we do a problem where we deal with a parameter of time like this that's a third variable when we're doing certain problems that are called related rate problems. Now, I don't need to show you how to do a related rate problem, but I can show you how to think about it and what happens. So a related rate problem is where you have somebody, you have a person, and say this person is flying a kite, all right? And as they are flying that kite, there are a couple of things that are going on. One is the string is going out at a rate, okay? There's a rate of the string. They're letting the string out so that the kite can fly, okay? So they let the string out. The other thing that happens is the kite is at a height, so it's at a basic height, all right? And that height changes based on how much string is out. So there is a rate that the height is changing, all right? And then in the same way, if you make this a right triangle, there's also a distance that the kite is away from you, and that distance is changing at a rate as well. So you can see all of these things are changing at a particular rate. Now, in fact, this distance will typically be like the wind, right? The distance the kite is away, that rate will be controlled by the wind. So it's like a wind rate that's pushing the kite away from you. And then there's a string rate that you let it out. And then sometimes what you want to do is you want to find how fast the height is changing or something like that. But all of these variables, distance, height, and then the hypotenuse, which is the string, they are variables that depend on time because that kite could be not quite as far away if it was a shorter amount of time. And so as time goes on, you release more string, the kite gets a little further away. And so all these variables in this problem, whatever they are, whatever's going on, they depend on time. So time is called a parameter, all right? And it's sort of the hidden variable. It's the variable that controls everything else. The longer the time, the more string, the further the wind has driven it away, the higher the height of the kite is. And that is what we mean by a parametric equation. There's like this hidden variable that controls everything. And what we typically do is we write them like this as a pair of functions, where x is a function that depends on time and y is a function that depends on time. And so you could have a very simple set of functions, something that would look like this. You might write x of t equals t plus 3, and y of t equals t squared, like that. And then you might say, gosh, the time is going to vary from, is going to be an element. Let's say the time is an element of the interval from 0 to 5 seconds. All right. And so then what happens is you can make a table of x and y variables and then graph this. And so, for instance, if the time, what I typically do is I add a third column. If the time is 0, then the x is 0 plus 3, and the y is 0 squared. If the time is 1, then the x is 1 plus 3, or 4, and the y is 1 squared. If the time is 2, then the x is 5, and the y is 2 squared, or 4. And then 3, and so forth. You could keep going on. And in this manner, you can see that the variables are changing at different rates. So if these were describing the height and the distance of the kite, the distance being pushed by the wind would be different than how the height changed. They would be changing at different rates. That's why it's called a related rate problem in calculus. So for those of you that take calculus next year, we'll solve these kinds of problems. And they're actually quite easy to solve. But they basically deal with parametric equations in disguise. Now, what we want to do is we want to take this information and we want to graph it. And so what would the graph of this look like? Well, we would first graph 3, 0, right there, and then we would graph 4, 1, and then we could graph 5, 4, and then the next one would be 6 and 9. So it would be up here. And so, we would do this all the way to 5. So at 5, t equals 5, we'd have 8 and 25. And so this graph is like a directed function. As time increases, we draw the graph in this direction until we get up to the point 825. And then we stop. It doesn't go forever. So you have to graph it over the whole domain. Although the domain could be all real numbers, and then you could just put an arrow to indicate that it goes forever. Okay? But this is how this kind of graphing works. It's fairly straightforward. All right? So one of the things that's emphasized in the homework is that parameters can be any variable. They don't always have to be time. And some of the examples they give are where they use a parameter of theta, just so you know. So for instance, you might have x of theta is equal to sine squared theta, and y of theta is equal to cosine squared theta. And so these are your parametric equations, and then theta is an element of the interval negative pi over 2 to 0. and then you would graph that. Now, one other point they make about this, if I was going to graph this, I would probably put theta, and then I'd put x and y. And theta, I want to be negative pi over 2. And if I plug that in, sine of pi over 2 is negative pi over 2 is negative 1. Negative 1 squared is 1. Cosine of negative pi over 2 is 0. All right. And then we could put 0. And sine of 0 is 0. And cosine of 0 is 1 squared is 1. Now, if these are the only 2 points we graph, we'd get 1, 0 and 0, 1. And that would be a pretty limited graph. We would think that the graph would connect those two and would look like that. However, if we make these smaller, often called the t-step on graphing calculators, if we make those numbers smaller, we tend to get a more accurate graph. So let's go from negative pi over 2 to 0, but let's go to it, let's put one more. Let's put negative pi over 4, which is halfway between those two. So then x, sine of negative pi over 4, is going to be a negative square root of 2 over 2, which when you square it is 2/4 or 1/2. So this is 1/2. And the cosine squared will be the same thing. So then you get 1/2, 1/2. So now you're right here. Oh, so now if you were connecting these in order, you would go up here and then down here. So now the graph is slightly more accurate. Now, what you could do is you could start to add more information, put more values in there to see what happens, okay? And so, you know, from negative pi over 4, you might want to put a negative pi over 3 and see what happens here, and so forth, and continue to sort of see what happens with the graph. So the graph, the first graph we just had these 2 points. We thought the graph looked like that. The second graph we actually had 3 points. We had 1, 0, 1/2, 1/2, and then we had 0, 1. So now we think the graph looks like that. Goes up to here and then down to here. And so it can get more accurate. So now I want to see, what does that graph really look like? And my sense of it is if I keep adding points, is it will look like this. It will go up to here and then straight down. That's what I think it'll do. Okay? And that might be slightly curved. But that's what I think it'll do. That's what I'm guessing. And so parametrics are a little bit hard to guess. So I want to show you this on a graphing calculator. Okay, so I have Desmos up here, and I'm going to show you how to do a parametric equation. So just before I do that, I made a little mistake on this over here that I wanted to mention. I was supposed to graph 0, 1, and I graphed 0, -1. So 0, 1 is going to be above the x-axis. So I apologize for graphing that. Everything's going to be on that diagonal line. Okay? So now let's go to Desmos and let's work on putting in a function. And so we'll see that we're going to put this function in right now. And the way you put the function in Desmos for a parametric is you do it as an ordered pair. So normally an ordered pair you would put in x comma y. So in this case our x was equal to sine squared of t, right? T is going to be our parameter here. And so we do sine squared of t, and then to get the squared there, I arrow back and hit the a squared. So now I have that, and then I put a comma, and then I put the cosine squared. So cosine, let's arrow, get the squared, go back and get the t, and now we enter it, and then what we have to do at that point is we enter the domain. And if you'll remember, our domain in this case was negative pi divided by 2 up to 0. And if we did that, you'll notice there's our 1, 0, and there's our 0, 1. Let me make this bigger. The 1, 0, you can see, in the 0, 1, not the 0, negative 1. How stupid of me. Anyway, and then the pi over 4 was the 1/2, 1/2 right in the middle. And so the next thing then would be, and I could even illustrate those points if you want. We could go 0, 1, and it'll put it on there. And then we can do 1, 0, and it'll put it on there. And then we could do the other point that we had, which was 1/2, 1/2. And I'll just do it in decimal because it's easier to type. And those were the 3 points we had. And we go from the 1, 0 up to the 0, 1 because we're going through that domain. Now, if we expand that domain, if we make the domain bigger, let's say, gosh, let's go from negative pi over 2 all the way to pi and go past the 0. How does that change the graph? And so now we're looking at, and nothing changed. Why is that? Okay, because the values repeat in the sine and cosine, and when we square them, they just repeat. So what's happening is we're just going back and forth on this line, okay? And that's kind of a big deal, and it's worth it for you to kind of think about what's happening. You go negative pi over 2 to 0, you go from 1, 0 to 0, 1, and then you go from 0 to pi over 2, and you're going to go back to where you started. So you're just going to go back and forth. So this parametric equation, and now I'm going to use my pen, all right? This parametric equation does this kind of thing. It just goes this way, and then it goes that way. So it creates a motion going back and forth, and no matter what the domain is, we're just moving back and forth. And now, if you make this like an object, like if you make it like an object and make it move according to this, then that object will move up to here, and then it'll move back, and then it'll move up to here, and it'll move back. So parametric equations are really good at creating motion and helping us observe motion of objects. And that's sort of their practical application. But in terms of graphing, that's how you graph. Now, let's just do just another one here. Let's go ahead and we'll just graph another one for kicks and giggles, and let's just make one up. All right, let's say the x value is pretty simple. Let's make it t plus 1. All right, and then we'll put a comma. And then let's make the y value, let's make it more complicated. Let's make it like a parabola. So we'll go, but just a little bit of a parabola. So t squared minus 3t plus 2. All right. Whoops. And let me delete that, and we want the outside parenthesis there. And now we want to know what t varies from. So t squared minus 3t plus 2 actually factors, t minus 1, t minus 2. And so it varies from 1 to 2. So let's vary it from 1 to 2 between the x-intercepts. And what we see is generated is we go from one x-intercept to the other x-intercept. All right? And we're shifting the graph 1 unit over. Okay? Because normally this would be from 1 to 2 on the graph, but now it's at 2 to 3 because we said t plus 1. That means we're adding kind of one value to the t before we plug it in. So it has the effect of moving things to the right, which is really interesting. You can start to think about that kind of transformation. Okay, and very often the first one, like x is just equal to t, and then you have that, and then you get the actual graph in the right place. But this is a way to do a shift, a transformation, and it works a little bit differently than what we're used to in regular rectangular coordinates. And so this graph is going to go from 2 out to 3. Now, if we expanded this, if we went, bigger, say to 5, then we're going to see the rest of the graph, right? And we're only going to graph that part of the parabola, and the motion goes from the intercept up to the end. And that would be the motion. Now, in the same way, if you made some sort of object, if you put some sort of object on here and you say, move that object according to this parametric equation, then you would see that object move on this track. Now, you could make it move backwards if you changed it and you went, well, you got to keep these in order because of the less than or equal. Yeah, so you can't just swap the values. So how would you make it go backwards on this? That would be, you'd take the negative of those parametrics and then, I believe, and make it go backwards, make it act in the opposite direction. So, but using parametrics is how you create motion. Now, that's not part of your assignment to do that. Your part of the assignment is just to come up with these graphs. And I recommend you do it by hand, make the table, t is, x is, y is, and plot some points, and then check it on Desmos. Now that you know how to put it on Desmos to make sure that you've done it correct. Okay? All righty. I'll see you later. Bye.